This is video 3 for the notes that we're doing over constant velocity vector problems. So we're going to look at example 10 in this video, and this again describes the movement of an object, and it says the object is initially at the point 510 and it moves with velocity vector 3i minus j. So they're just tossing in one where they gave it to you in the vector in unit vector form rather than component form. And notice that the units here are meters per minute. So before we jump into the problems, let's just kind of draw a picture of what that looks like. So you're going to find that I'm not even sure why they did all these examples that are pretty much, the pictures look pretty much the same, but that's all right. All right, so this one says that it's initially at the point 510, so let's just kind of, I'm just eyeballing it here. This does not have to be exact. So that's its initial position. And then it's moving with this velocity vector 3i minus j. So in component form, that would be 3, negative 1. And we can see that what that means is it's moving over 3 and down 1, over 3 and down 1. Again, I'm just estimating this, but you can see then that, you know, that we're moving with this constant velocity like this. So that just gives us an idea of what's going on. And so what they want in A is they want the position of the object at time t. So what they're looking for here is that position equation, vector equation. And so we can just call the position xy. And we know from our past problems that the first vector we want is the initial position vector, so that's 510, plus, and then we'll have t in time, that's what they tell us to do, time per minute. And then we need our velocity vector, which is in meters per minute. So that's going to be 3, negative 1. And again, I just want to emphasize the units here. So the units for this one, remember, we're in minutes, right? They tell us right here, time is in minutes. This is in meters per minute. And so, of course, when we multiply those together, we'll get meters. So this is also in meters. So the position is being given meters. And then, of course, this will be in meters. And then notice that actually, we're going to go a little bit further with this. The position is going to be a point, right? So we're going to take this a little bit further. So if I write this in parametric form, that means that x is going to be equal to 5 plus 3t, and y is going to be equal to 10 minus t. And so its position is going to be an ordered pair. And so the position will be the ordered pair 5 plus 3t, 10 minus t. Okay, so that's what they're really looking for when they ask for the position. All right, then for B, they ask us for the speed of the vector. And so the speed we know is going to be the magnitude of the velocity vector, which is 3, negative 1. So that's going to be the square root of 9 plus 1, so the square root of 10, right? And that also will be in meters per minute. In question 3, it says, okay, so what is the position at time equal 3? Well, here's our general position formula right here. And so the position at time equal 3, we're just going to sub in 3 for time. So 5 plus 3 times 3, 10 minus 3. And so that's going to turn out to be, what, 14, 7. Okay? And certainly you could have subbed, you know, the 3 back into this formula also, or this one, you know, it doesn't matter. I subbed it in here, but you can put it into any of those. But notice that your final answer, because it's asking for position, is going to be an ordered pair like I have here. All right, and then the last one says, find the time when the object is due east of 0, 0. So this one, I think you really do need to have a picture so you can visualize what's going on. So here's 0, 0, and being due east means that I'm going to be along here somewhere. So it means now it's reached basically the x-axis. Well, what do we know about every point on the x-axis? Well, we know the y-coordinate is 0 everywhere. So basically what we're doing is we're just taking this particular equation and setting y equal to 0. So we have 0 is equal to 10 minus t, and so adding t to both sides, t is going to be 10, right? And that is going to be in minutes. All right, so then it says, so it just says find that time when it's due east, and that will be at 10 minutes. I think we'll just go ahead and finish this last example in this video. So this says, find the velocity vector of a swooping eagle moving in this direction. That shouldn't have been split, but the direction vector is -2, 5, -14, with a speed of 90 kilometers per hour. All right, so remember, this is our direction vector, all right? This is not necessarily our velocity vector. So it's telling us we're going in that direction. So what we would want to do is find out, well, what's the magnitude of this particular vector? So we'll find the magnitude of -2, 5, -14. And so that, of course, is the square root of 2 squared, -2 squared, which is 4, 5 squared, which is 25, 14 squared, which is 196. So we end up with the square root of 225, which is 15. All right, so there are two different ways that you can finish this. You could say, well, this represents then 15 kilometers per hour, but we need to be going 90 kilometers per hour. So since 15 goes into 90 6 times, we would just need to multiply that by 6. So therefore, our velocity vector is going to be 6 times -2, 5, -14. And so that would give us -12, 30, and then -84. Okay, or remember the way you can think about it is you've got this vector, -2, 5, -14. So it's 15 units long, however long it is. But we want to turn it into a unit vector first. So that means I can multiply it by 1/15. So now I have this little unit vector right here going in the same direction. But now I need for it to be 90 units long. So I'm going to multiply that by 90. Well, again, you can see that this gives you 6. And so we end up in the same place that we were before, and we end up with the same answer.